In today's video lecture, we are going to begin the packet of notes dealing with first-order RC and RL transient circuits. This is covered in the book in sections 7.1 through 7.6. We're going to begin by briefly talking about what we mean by transient response to begin with. Then we're going to look at two different classes of circuits. The first class is what we call source-free RC and RL circuits. These are circuits where after a specific point in the circuit, there are no sources present. The second class are driven RC and RL circuits. These are circuits where after a certain point in the circuit, there will be a source present. We're going to see that in both of these cases, the voltages and currents in the circuit follow an exponential decay. So we're going to look at a lot of the properties of exponential decay. We're going to end up by looking at what happens with circuits where you have multiple changes in the circuit. We call those multiple abrupt changes. Before we get into any details, I think it's useful to look at a very simple example. The example we're going to look at is a flash circuit in a camera. This example is extremely simplified, but I think it illustrates the idea behind transient response. So how does a flash work in a camera? Well, you're going to have a little battery in the camera, call it Vs, that will have a series resistance, call it Rs, that's going to be connected to an energy storing capacitor, call it C, through a switch. You're also going to have over here a light bulb or a flash. Before you take your picture, the circuit is sitting like this and this capacitor is collecting charges. The battery is charging up the capacitor and it is sitting there in DC steady state. So let's draw over here. So the voltage across the capacitor, which we will call Vc, is at Vs. When you take a picture at, let's say, time t1, what happens is this switch is going to move from that position to that position. That is at time t1. What happens now is this energy stored in the capacitor is going to get dissipated through the light bulb. In other words, this capacitor will very quickly dump all of its stored charge through the light bulb, lighting it up so that you can take the picture. What happens then as the capacitor loses the charge, it will quickly lose its voltage. So its voltage is going to go down like that pretty quickly. When the picture is done, what happens then at time t2, and I forgot to label T1 here. At time T2, the switch goes back to the first position and the capacitor can now recharge. So what happens at some time T2, after the picture is done, the capacitor is reconnected to the battery and slowly it builds up the charge again until once again it is sitting at a voltage of Vs. So we have three distinct areas here. On the left, we basically have DC steady state. The capacitor is charged. In the second part, we have a decay to zero, and this is the flash. In the third part, we have another exponential rise, and this is the recharging. And of course, once you're totally recharged, you return back to DC steady state. Well, it turns out that these two parts of the circuit here, the flashing part and the recharging part, are both transient responses. So in this packet of notes, we will look at how to analyze circuits mathematically to determine exactly what happens during these changing parts of the circuit. So once again, what we mean by transient response is time changing. So transient just means time changing. In the previous packet of notes, we looked at many different properties of capacitors and inductors, and one of them was DC steady state. We saw that if a circuit was sitting there a long time with a DC voltage or current source, the capacitor eventually looks like an open circuit, the inductor looks like a short circuit, and they both are storing energy. What we're going to look at in this packet of notes is what happens when there is a sudden change in the circuit so that you no longer have DC steady state. The change in the circuit could be due to a lot of things. You could turn off your sources. You could switch them out of the circuit, as we did in the example on the previous page. You could even do things like add resistors or remove resistors. Basically, any change in the circuit causes the DC steady state to disappear. So what happens is the energy that you have in whatever capacitors and inductors are in the circuit will adjust themselves to cause the circuit to reattain steady state. And this is what gives us our transient response. So basically what we're going to see is solving these circuits for the transient response amounts to determining what the initial steady state value was, finding out what the new steady state value is going to be, and then figuring out what happens in between in what we call the transient response. In this packet of notes, we're going to focus on circuits that have only a single capacitor or a single inductor. We call these first order RC and RL transient circuits. To have a first order RC or RL transient circuit, you need a couple things. First off, you need at least one resistor. You could have more than one, but you need at least one. I should point out that it can either be a physical resistor or it can be some other electronic device that acts like a resistor, such as a light bulb. The second thing you need is a single capacitor or an inductor, but absolutely not both. If you have a capacitor, you're going to have what's called an RC circuit. If you have an inductor, you're going to have what's called an RL circuit. The third thing that you need is a change at time t0. You either need the source to disappear, you need a source to turn on, you need the source to change, you need to add a resistor, you need to remove a resistor, something. You need some change in the circuit at some time t0. Otherwise, you're just going to have a DC steady state circuit. I should point out here that for math ease, we usually are going to have t0 equal to 0. We're going to call time 0 as the time when the circuit changes. It does not have to be at time 0, however. What we're going to see in the next few pages is that when we analyze these first order RC or RL circuits, you're going to get first order constant coefficient differential equations of this form. X prime plus AX equals some function f of t, and this f of t is going to depend on the input signal, the sources. And these differential equations are also going to have an initial condition. To solve these first-order differential equations, you have a couple different approaches. In EE210, we're going to look at a very classical method for solving them. For those of you who are going to take 350, you will learn how to use the Laplace transform to solve for them. Okay, let's do a little review of Math 250. Very little review, because we are going to be using differential equations here. Hopefully you remember from Math 250 that when you solve a first-order differential equations, you get two parts, what we call the homogeneous solution and the particular solution. Those are math terms. In engineering, we call it the natural response and the forced response. Basically, the natural response is the same as a homogeneous solution. The forced response is the same as the particular solution. So what are the physical meaning of the natural response and the forced response? The natural response is basically the transient response. This is based upon the circuit's desire to reattain steady state once it has been disrupted. The forced response, then, is the new steady state after the transient part dies down. We're going to look at two basic classes of circuits in this set of notes. We're going to first look at source-free circuits. This is a little bit of a misnomer. When you think source-free, you may think of a circuit with no sources whatsoever. Actually, what we mean by source-free is that there's going to be no voltage or current sources after T0. Remember what T0 is. T0 is the point in time where the circuit changes. Voltage or current sources will certainly be present before T0 to either charge the capacitor or energize the inductor, but then after T0 there will be no sources present. We're going to see that when we have these source-free circuits, we get only a natural response. The other class of circuits we're going to look at is driven circuits. Driven circuits are those where there will be at least one voltage or current source present after the discontinuity T0. There may or may not be sources present before T0, but you have to have at least one source present after T0 to have a driven circuit. Driven circuits we're going to see have both a natural and a forced response. We're going to start by looking at the easier of the two cases, the source-free RC and RL circuits. Once again, I want to make sure you remember that this means there's no source present after T equal T0. So what happens in a source-free RC or RL circuit? You're going to have a capacitor charged in DC steady state, or you're going to have an inductor energized in DC steady state. And then when you remove the source, basically the capacitor or the inductor is going to act like a temporary source. The energy that is stored in either the capacitor or the inductor will slowly get dissipated through whatever resistors are remaining in the circuit, and eventually the energy will go to zero. We're going to see that the underlying differential equations in this case are x prime plus ax equals 0. In other words, this forcing function f of t is 0 because we are source-free. Furthermore, we're going to see that the solution is always going to be a decaying exponential. We're going to have a constant at some time T0. We're going to get a decay to 0. I think the best way to illustrate this is with a couple examples. So we'll start with an example where we have a voltage source Vs, two resistors R1 and R2, and a capacitor C. We're going to have a switch in the circuit right here, and at time 0, the switch is going to open up and disconnect the voltage source in R1 from the capacitor and R2. And we're asked to determine an expression for the voltage across the capacitor using whatever tools we can. The way we're going to analyze this circuit is we're going to break it down into two distinct times. First off, for t less than 0, this is a DC steady state situation. Circuit has been sitting around a long time before 0, so we're going to have a voltage source, a resistor R1, a resistor R2, and the capacitor, because we are in DC steady state, the capacitor is going to look like an open circuit. It will have a voltage across it, Vc, but it will not have a current. The voltage across the capacitor right before the switch is flipped is Vc at 0 minus. Remember this notation we introduced in a previous lecture. This means the moment right before time 0. Vc at time 0 we can get from voltage division. It's R2 over R1 plus R2 times Vs. We're going to call this Vc naught, and this is our initial condition. We're going to see that this value is very important. The second time range is for t greater than or equal to 0. This is going to be our transient part. At time 0 is when the circuit is changing. So for t greater than or equal to 0, all that's left in the circuit is this resistor R2 and the capacitor. The capacitor is no longer a DC open circuit because we are not in a steady state situation. We still have a voltage across the capacitor, Vc. I'm going to use a T in here to illustrate the fact that it is going to be changing with time. And of course, we're going to have a current through the capacitor. Let's call it IC of T. To analyze this circuit, let's do KVL. Let's start at this point down here. Let's go through the resistor and then through the capacitor and see what we get. Going through the resistor, we're going to get a voltage drop because the current through the resistor is going in this direction and it's IC. The voltage across that resistor is going to be R2 times IC of T. So using KVL, we get R2 times IC plus Vc is equal to 0. But we also know that there's another relationship between the current through the capacitor and the voltage across the capacitor, this differential relationship. So we can plug the second equation into the first one to get this. R2 times C times dVc dt plus Vc is equal to 0. Finally, we can divide everything by R2 and C to get dVc dt plus 1 over R2 times C times Vc equals 0. Notice we get a differential equation of the form Vc prime plus some constant A times Vc is equal to 0. Let's try to find a solution to this now. So we have Vc prime plus A, which in this case was 1 over R2C, times Vc is equal to 0. If you think back to Math 250, what function Vc of t has a derivative that is the same form as the function itself, so that when you add the function to its derivative with some scaling, you can get 0? The answer is an exponential function. So we know that the solution has to be of the form Vc of t is some constant A times e to the st. And we have two unknowns, this amplitude A and this coefficient S. Let's plug this back into this equation and then try to solve for A and S. So the derivative of A e to the st is Sa e to the st. So we get Sa times e to the st plus 1 over R2C times A e to the st has to equal 0. We can factor out the A e to the st and we get S plus 1 over R2C times A e to the st equals 0. For this expression to always be equal to 0, this thing in brackets must equal 0. This means that S has to equal minus 1 over R2C, which means that Vc of t now has to be A e to the minus t over R2C. We still need to figure out what A is. To do that, we're going to use our initial condition. Recall that we know the voltage across the capacitor at 0 minus was R2 over R1 plus R2 times Vs. We got that from the DC steady state part of analyzing the circuit. But we also know that with capacitors, the voltage across the capacitor cannot change instantaneously. That means that Vc at time equals 0 plus also has to be that same value. So even though the circuit changes abruptly at time 0, the source and R1 are switched out of the circuit, the voltage across the capacitor cannot change instantaneously. So this is going to help us get A. What we do is we evaluate the function at time equals 0 plus. So Vc at 0 plus is going to be A e to the minus 0 over R2C, but its value has to be R2 over R1 plus R2 times Vs. E to the 0 is just 1, so we know that A has to be R2 over R1 plus R2 times Vs, which if you look back to the previous page, that's what we call our initial condition, which we abbreviate IC. So putting that together, we know that the voltage across the capacitor is now given by this expression here. We can generalize this solution for any source-free RC circuit. So the general form for a source-free RC circuit with a change at t equals 0 is going to be Vc of t is going to be some Vc naught times e to the minus t over tau. This Vc naught is an initial condition. This tau is something that we call a time constant, which we will look at shortly. The Vc naught tells us how high the voltage is initially. The tau controls how quickly it decays to 0. So we're going to have a situation where we have DC steady state up to here with some value Vc naught. At time 0, when we're removing the source from the circuit, all the energy that is left in the capacitor is going to get discharged through whatever resistors are present in the circuit, and we're going to get this exponential decay. Let's look at one more quick example. Let's look at a source-free RL circuit. So in this example, we have a current source, 2 resistors, and an inductor. And just like the previous example, we're going to have a switch. This switch at time 0 is going to open up and disconnect the current source and R1 from the inductor and the remaining resistor. Like the capacitive case, we're going to break this circuit into 2 distinct periods of time. For t less than 0, we have DC steady state. We're going to have current source, R1. The inductor in DC steady state is a short circuit, so it will have a current IL, but it will not have a voltage across it. And then a resistor, R2. The current through the inductor right before we flip the switch, is simply just going to be IS in this case. What happens? The current coming out of this source can go either there, there, or there, but because of the short, all of the current is going to go through the inductor, and you have no current there and no current there. So in this example, IL of 0 minus is IS, and once again, we're going to call this IL naught. This is our initial condition. After the discontinuity, after the switch is thrown, the left resistor is gone, and the current source is gone, and we just have the inductor and R2. Notice once again, just like in the capacitive case, the inductor is no longer a short circuit, it is now an inductor. It's going to have a current, IL of t. It's going to have a voltage, VL of t. And notice the passive sign convention is upheld for the inductor. The current through the inductor, IL, is defined as the current into the plus terminal of the inductor. Let's analyze this circuit. Let's do KCL at this node up there. Basically, this current plus that current has to equal 0. So from KCL, the current to the left is IL of t. The current to the right is the current through the resistor. From Ohm's law, the current through the resistor is the voltage across the resistor. And since the resistor is in parallel with the inductor, VR is VL. So the sum of those two currents equals 0. But we know that there's another relationship between IL and VL. Specifically, we know that the voltage across an inductor is always L times the derivative of the current through the inductor. Combining those equations together, we get L over R2 times DIL dt plus IL is equal to 0. We can now divide everything by L over R2 to get DIL dt plus R2 over L times IL is equal to 0. What we notice is, like the capacitive case, we get a differential equation of the form IL prime plus A times IL is equal to 0. We can try to solve this problem the same way we solved the capacitive problem. We'll assume a solution of the form IL of t is A e to the st. Why does it have to be that form? Because exponential is the only function whose derivative is the same form as a function itself. Plugging this back into here, we get SA e to the st plus R2 over L times AE to the st is equal to 0. So you get S plus R2 over L times AE to the st is equal to 0. For this to be equal to 0, the part in bracket has to equal 0, which means S has to be minus R2 over L. So IL of t is AE to the minus R2 over L t. To get A, we're going to use our initial condition. We know the current through the inductor right before the discontinuity was equal to the current source in this case, but because the current through the inductor cannot change instantaneously, IL of 0 plus is also equal to IS. So once again, this is our initial condition. Solving this function here at t equals 0 plus, we get IL of 0 plus is A e to the minus R2 over L times 0, but that has to equal IS. E to the 0 is just 1, we then get that A just equals IS. So IL of t in this example is IS times e to the minus R2 over L times t. This is a specific answer for this circuit. The general equation for any source-free RL circuit is the current through the inductor after the discontinuity is some initial condition times e to the minus t over tau. Once again, there are two key parts here. This is the initial current, and this tau is going to be the time constant. It's going to dictate how quickly the current dissipates to zero. So plotting this, we're going to have a constant current up to time zero, so our initial condition, and then at time zero, the current is going to decay exponentially like that. So let's summarize the results that we have for both the capacitive and the inductor cases. In both cases, we're going to get a differential equation of the form x prime plus ax is equal to 0 for t greater than or equal to t naught. In those previous examples, t naught was 0, but it does not have to be 0. We also saw that we have an initial condition of x at time 0 plus with some x naught. So let's look at the two cases now. In an RC circuit, for t greater than 0, you're always going to have a capacitor and some Thevenin equivalent resistance. In our example, it was a single resistor, but it doesn't have to be a single resistor, as we're going to see in some later examples. It could be resistors in parallel, in series, or any combination. But regardless of how many resistors you have present, you can always model it as a single parallel resistor to the capacitor. And we're going to see that you have initial voltage across the capacitor, Vc naught. Likewise, in an RL circuit, you can always model it as an inductor in parallel with a Thevenin equivalent resistance, once again with an initial current through the inductor of IL naught. These two values come from DC steady state before t equal t naught. We then saw in both cases we're going to get a differential equation of the form x prime plus ax is equal to 0, which in the capacitor case was this, in the inductor case was that. So in a capacitor case, A was 1 over RC, in the inductor, A was R over L. We then saw that the solution to these differential equations was always a decaying exponential. And once again, what we saw is that the amplitude was this initial condition. We also saw that this tau, what we call this time constant, which we'll look at in more detail, was just the reciprocal of A. So for an RC circuit, it's RC. For an RL circuit, it's L over R. Final comment I want to make is we're assuming a discontinuity at time t naught here. So notice this term here, rather than just being t over tau, it's t minus t naught over tau. So that's going to be the only major difference between a discontinuity at 0 and a discontinuity at another time, is that if the discontinuity happens at some time other than 0, this t term is going to be t minus t naught, where t naught is the time of the discontinuity. What we see in both cases is we have a decaying exponential. So let's try to understand intuitively what's happening in these source-free RC and RL circuits. As I said, before the discontinuity, before the sources are removed from the circuit, the capacitors and inductors are being energized. Capacitor is charged up to its full value. The inductor is energized to its full value. So they store energy. What happens then, once the switch is thrown or the source is turned off and removed from the circuit, all that energy that's stored in the capacitor or the inductor is released through the remaining resistor or resistors. What happens is those resistors dissipate energy. And so all the energy stored in the capacitor or the inductor will get dissipated, and we end up with another steady state with no stored energy. So whether we're talking about the voltage across the capacitor or the current through the inductor, we have a situation where DC steady state, here we have our change in the circuit, this time here, and then we have our exponential decay as the energy gets drained from the capacitor or the inductor. If you want, you can think of capacitors and inductors as temporary voltage or current sources. A capacitor would be a temporary voltage source, an inductor would be a temporary current source that die out exponentially because their stored energy is not being replenished. One final important point is down here. Although these two examples we were calculating the voltage across the capacitor and the current through the inductor, the reality is that every voltage and every current in these RC and RL circuits will follow the same decaying exponential shape. They might have different amplitudes, but they will all be decaying exponentials. Because this decaying exponential is so important in these RC and RL circuits, we need to spend some time looking at properties of the decaying exponential response. So we saw that whether we're talking about RC or RL circuits, we're going to get voltages and currents of this form, x naught e to the minus t over tau. Let's look at this in more detail. We're going to look at a normalized exponential decay. It's going to be normalized in amplitude by dividing it by x naught. In other words, we're basically saying it's going to have an amplitude of 1. We're also going to normalize the x-axis by not plotting it versus t, but plotting it versus t over tau. In other words, one way to look at it is this 1 basically means 1 time constant, or tau. 2 would be 2 time constants, or 2 tau. Likewise, 3 tau, 4 tau, 5 tau. So this is what a normalized exponential decay looks like. In other words, this function here is just e to the minus t. We're normalizing it with an amplitude of 1 and a time constant of 1. What we're going to see here is after 1 time constant, so when t over tau is equal to 1, the value is 0.3679, or approximately 37% of the initial value. What this means is that between the start of the exponential decay and 1 time constant later, basically the voltage or current decays to 37% of its initial value. In other words, it drops 63% of its value. By the time we get to 2 time constants, the value e to the minus 2 is 0.1353. We're down to 13.5%. But another interesting thing is the value here is 37% of the value after 1 time constant. And we're going to see that every time you move another time constant away, it's going to be 37% of the previous value. So this point here was 37% of that. This point here is 37% of that. After 3 time constants, e to the minus 3 is 0.0498, or 5%. So that is 5% of the initial value, or 37% of the previous time constant value. After 4 time constants, e to the minus 4 is 0.0183, so this value is 1.8% of the initial value, or this value is 37% of that value there. Finally, by the time you get to 5 time constants, e to the minus 5 is 0.0067, and so this value is less than 1% of the initial value. It is still 37% of the value here, but it's so small we can't even see it. But here we get this very important result. We say that after 5 time constants, our transient response is over. This function here technically never equals 0. But by the time we get to 5 time constants, its value is going to be so small, less than 1% of the original value, for all intents and purposes, we say that it is 0. Regardless of what the time constant is, by the time you get to 5 time constants, the transient response is over, and we return to DC steady state. This figure illustrates what's going to happen now when you have time constants plotted not t over tau, but versus time. In this green waveform, the time constant is 0.1 seconds. So by the time it gets to 0.5 seconds, it basically is down to 0. Technically, it's never 0, as I said before, but for all intents and purposes, we say it's going to be 0. In this blue waveform, the time constant is 1 second. So now it actually takes 5 seconds to get to 0. And the red waveform, the time constant is 10 seconds. It would take 50 seconds to get to 0. So bottom line, if you're plotting the response on a normalized plot, which is what we did here, t over tau, it's always going to go to 0 at 5. If you plot it on a non-normalized plot, such as here, it could go to 0 at 0.5, or at 5, or at 50, which is a couple pages away from here. But this gives us some physical meaning to this number tau. Tau tells us how long it takes to slow down. The larger tau is, the slower the rate of decay. And remember, it takes 5 time constants to get to 0. The final property of the exponential decay that we're going to look at deals with the initial slope. So here we have an exponential decay, looks like this. And this is the function x naught e to the minus t over tau. Its initial rate of decay is this tangent line right here. What we see, though, is if you take the derivative of this function, dx dt, you get that. If you evaluate that at t equals 0, e to the 0 is 1, you get that, which means the slope of this tangent line is minus x naught over tau. This is rise over run. Since that's x naught, that is tau, we get this very interesting result. The tangent line of the initial slope of decay, if you extend it all the way to the x-axis, it hits at tau. So the tangent line intercepts the time axis at a typo that's supposed to be tau, not t. We can generalize this, by the way. Let's look at a situation where the decay does not start at 0 but starts at t naught. you still have this tangent line. The slope is still going to be x naught over tau. So that length is tau. So it's going to hit at t naught plus tau. We will see later on in this packet of notes how this property of the exponential decay is actually useful in helping us approximate what the time constant is. Next lecture, we will come up with a formal algorithm for solving RC and RL circuits, and then we'll do lots of examples. Have a good day.